Hi, my name is Brian Walker. I'm with Copper Mountain Technologies, and today I'd like to demonstrate the time domain measurement feature of one of our vector network analyzers. What I have here on the table is an S5048 that is a 4.8 gigahertz vector network analyzer, and it starts at 20 kilohertz. So on my screen here, I have S11 being measured from 20 kilohertz to 4.8 gigahertz. Now I'm going to make some changes. I'm going to do the setup required to give us a time domain measurement. I'm going to do a low pass time domain measurement with a step function. Now there are choices there. The band pass method is used for time domain measurement through a limited bandwidth such as a filter. The impulse measurement is good for looking at changes in impedances. But I'd like to see the step function because it gives us more information, and the low pass type of time domain measurement gives us even more information if you have access to measurement all the way down to zero. So I'll go ahead and set this up, and the stop frequency that I have on the board here is going to remain 4.8 gigahertz, which is the top end of the VNA. The number of points I'm going to set to 800. And now, because my top end is 4.8 gigahertz, the resolution in my time domain is going to be 1 over 4.8 gigahertz, or 208 picosecond. Now, for the number of points at 800, we have to set the start to 6 megahertz. We have to do that so that every point on the screen is harmonically related. Now, I can do that very simply by going to Analysis, Time Domain, Set Frequency Low Pass, and it set the start frequency to 6 megahertz for me. I could have just entered it. So now I'm just about ready to go. I have not calibrated the VNA, and I've done that for a reason. It's calibrated at the factory. It's calibrated at the factory to the ports. And I actually want to measure from the port through this first cable, this first 50 ohm cable, through these adapters, and then into this 75 ohm cable. So we'll see a nice transition, and then we'll see a different impedance for the 75 ohm cable. And if I calibrate it to the end of the 50 ohm cable, well, it would take that cable out of the picture. We would not see it. We'd only see the 75 ohms. So I want to see everything. So without any cal, my cal plane is right here at the port. So let's do the rest of the setup. I'm in the time domain mode now. I'll start again, Analysis, Time Domain. I'm going to set the units to feet because I'm interested in distance. The reflection type, signal goes out and comes back. I don't want the two-way time, I want the one-way time. I want to know what's happening at each distance. I don't want twice it, so one way. I'm going to turn on cable correction. That'll get me the correct distance versus time. So the velocity factor for Teflon is about 0.7. I'll turn that on. And now I'll turn the time domain feature itself on. The start I'm going to set to 0. The stop I'm going to set to 8 feet. And I'm going to have low pass step. And now I am properly set up. Now what you're seeing on the screen is this. Actually, I need to go out a little bit further. There. What you're seeing on the screen is for the first 3 feet, you're seeing my good 50 ohm cable, and its return loss is, well, it says about 40 dB. It's pretty good. Then I've got these transitions, which is this bunch of adapters, and then I'm transitioning to a 75 ohm cable, and I see a return loss here of about 13.9. I can put a marker on it and measure it. And it's about 14 dB. So if you do the calculation, because I'm on a 75 ohm cable, the return loss on a 75 ohm cable is, the reflection coefficient is 0.2, and the return loss is 13.9 dB or roughly 14. So we're actually seeing the reflection coefficient of that cable. In the time domain here, the first 3 feet, we see the 50 ohm cable, and then 1, 2, 3, 4, it's like 5 feet of 75 ohm cable, and the 75 ohm cable is then open, and so we see the 0 dB return loss, complete reflection from the end of the 75 ohm cable. So this is giving us a good view through this entire cable. And if this had been a cable going up to the tower to, let's say, a land mobile radio antenna, we'd be able to analyze the return loss of that cable all the way up the tower. And we'd be able to see if there was, say, water in the coax or if there was some other failure of the cable itself. I can introduce a kink in the 75 ohm cable, and you can see it right here. So there's a defect that I'm creating by crimping the 75 ohm cable. And I can locate that in distance. I put a marker on it. It is 6.4 feet down this entire cable system. So it would make it very easy to find if it were a defect in a cable, say in a wall or some other hard to get to place. So I've demonstrated how to show return loss over distance. Let's do one more thing. I'm going to do Z conversion. That'll allow us to see the characteristic impedance over distance. So I'm going to turn conversion on. I have to get out of log mode now and go to linear magnitude. And now I have to change my scale. So the reference value is going to be 50 ohms and 10 ohms per division. I'll pull that down a little bit. And now you can see that I have a 50 ohm, well 49.0 ohm cable for the first few feet. If I move my marker along, or add a new marker, you can see I'm measuring 72 ohms on the 75 ohm cable. So I'm actually measuring the impedance of the cable over distance, 50 ohm, the adapters. I can see reflections from those adapters. I can see the characteristic impedance of the 75 ohm cable, and then the open end of the cable where the impedance is undefined and it just goes up. So we're able to measure return loss over distance or over time, and we're also able to measure the characteristic impedance over distance or over time. Thank you.